Today's lecture is about scaling up and big data. Until now, we have talked a lot about images. That images can be large, big, that can be a lot of data, but not really talked about the framework, how to handle this amount of data that could come in from the experiment. So this is what today's lecture is about. And so first, a little bit of lecture. Today, we don't have John Ross, but a lot of other references, mainly slides, lectures online on YouTube about how Google is working with distributed computing, tutorial on Hadoop, etc. There's also one intro to data science. But that's it's a link to actually a class, but there are some videos on that one too. Also on cluster computing, same concept. There is a paper and quite some information otherwise. And also databases, just a paper to read about the databases and how to handle it for image analysis. Cloud computing, Amazon S3 is a huge cluster where you can buy in time. You have some free time and you have or you can buy time defining. You can define what kind of computational power you want to use in your project. And then also here in this topic, there is also a couple of references that you can read. So today's outline, we have some motivation, some principles on computer science, organization of how to work with this amount of data, big data, some frameworks, how to work with it, cloud computing, and then looking into the future, what could come, what would be needed in different types of experiment. So first of all, as you already know, we can have pretty big data sets. So really big data sets, we have a lot of memory. We can't fit it into memory possibly. Most computers don't have more than 256 gigabytes of RAM. Hard drives, a couple of terabytes is not unusual to have on big workstations, but more than 256 gigabytes of RAM is pretty rare, and it's also really expensive. On your normal desktop workstation, you may have 64 gigabytes if you're going in the luxury line. But otherwise, usually groups have dedicated workstations with more memory for bigger processing. Also, many computers don't have more than 16 cores, and that would, in the case of 256 gigabytes, that would give about 16 gigabytes per CPU if you would split it up. Then it's also a question about speed of secondary storage. How fast are your speeds? How fast is your network access to servers? And possibly if something crashes, then you may lose everything you have processed until that point, unless you manually write a lot of checkpoints throughout your processing. So that's the big data set problem. And then on the other side, we also have many data sets. So for example, you have thousands of samples that you want to study. And in dynamic experiments, you may have a series of hundreds of measurements. Also at phenotyping, you can have thousands of several hundred gigabyte data sets. And as a reference, a radiologist in Switzerland alone could produce about a petabyte of scan data per year. So that's a huge amount of data to handle, and also many data sets. The last thing is doing exploratory studies. So you're not really sure, you know something behaves in the sample, but you're not really sure what you're looking for. And that also produces a lot of data, because you have to capture data that covers at least your main hypothesis. But then you also may have to develop new analysis techniques, also doing quick tests on the data. Just grab a little sample somewhere and do an initial analysis in order to do this study. So one example project is the zebrafish full animal phenotyping. So we have these little cute zebrafishes, and a tomography set of 1,000 of fishes results in data sets looking like this one that I'm slicing through here. The resolution is below a micron, so the images are 11,000 by almost 3,000 by 600 voxels, and that is 20 to 40 gigavoxels per sample, a huge amount, and you can't really handle it. Just think about if you want to apply a filter on this, you usually work in floating point data, and the question is, you need to convert the whole data set into floating point, because that would multiply the number of voxels by a factor 4, because you need 4 bytes at least to represent the floating point. So it's a really huge amount of data. Some filter also require that you have intermediate storage for the filtering. For example, the ISS filter I mentioned in the image enhancement lecture, I think it takes about 5 times the image, and that times 4. So it's really a lot of data that it's stored within this kind of filtering. So with that, you would probably even blow out the a full 256 gigabyte computer in just a single filtering process. So you need to split it down, and that's kind of the keyword: split it down into smaller pieces and work on those. So it's a little bit divide and conquer approach. Then the objectives of this experiment was to identify single cells without any downsampling. So that would be really working on the full data set you have. Then look at different cell networks and their connectivity, classification of different cell types, and registration of histology in the data. So there are a couple of questions that need to be handled within this data set. And sometimes we need to go on a very detailed level, but still, when we go on the details, we can focus on smaller regions. And that's always important to think about. Another project is the brain project. So also the brain in an experiment was scanned at cellular resolution. 1 cubic meter at 1 micron produces 1,000 gigavoxels per sample. And that's also a huge amount of data. And here it's about also registration about separate scans and make sure that they are connected. And the idea is to look for blood vessel structure and their networks. In combination with that, we have the bimodal approach, combining with the functional MRI and histology information. So it even adds more information to the problem. And then we really go to the limits of at least what the workstation can do. and also on the full data set. So what is wrong using the usual approaches? So initially, we would take a couple of steps. We apply a filter, maybe a median filter with some neighborhood. Then we apply a threshold of 10 or something. Then we want to have some components that we want to identify. We can label them, and we can count how many there are in each component and save it to file. So that would give some kind of example code that you see below here. Makes sense, but this is maybe not useful when we go up to bigger things. So if you would like to do a change in the workflow, you want to change what happens if you exchange the median with a Gaussian, or you want to compare how the two are working. You want to see what happens if you look at 3D instead of 2D. In general, if you have three-dimensional data, use that information. So don't boil it down to 2D, because usually you lose information then. And then it may be that you want to run the same analysis on all images in a folder. And that is also, then you also need to add your framework, make it more flexible. So if you use the standard approach, you would have to write a little function or a little script for everything you change. And that's not really easy to work with, particularly when you start with big data and want to have reproducible data. And therefore, you need to really think about, before you start coding, think about how will it be used once I have the final implementation. And keep that in mind all the time, allowing you to, maybe it's a little bit more complex code on some places, but still you would gain in the end, because when you start to multiply the whole work, then you really want to have something that you can have a little bit more flexible and not having to rewrite everything, or maybe even dynamically rewrite whatever. So that is important to think about. Think before coding. Now we switch over to how to handle the whole thing. A little bit about computer science. So there are whole educations about computer science. So I can't cover that in a whole in about half an hour lecture part. But anyway, in principle, the topics that are relevant in this context is that, first of all, we need to work in parallel. And taking that one level higher would be to work distributed. And then we have the question about resources, how to handle the resources and work with them in an efficient way. And depending on which kind of approach you work with, there is the imperative kind of coding or problem solving, and the declarative. And I'm going to tell a little bit more about them soon. So first of all, what is parallelism? In principle, it means that you can divide a task into several subtasks, and those can be worked in parallel. And hopefully you, in the end, would come quicker to the goal than if you would do them one after the other. A very simple daily example would be if you have to walk for 5 minutes and talk on the phone for 5 minutes, you can do it one after the other. Sometimes it makes sense, actually, but you can also do them in parallel. So walking and talking, most people are actually able to do that. That will save you 5 minutes. And so some tasks like this one are very easy to parallelize. Other ones are very difficult. And in particular, when it becomes difficult is when different pieces of parallel code need information from each other. And as soon as you need to exchange between the different tasks, then it gets very hard, and you need synchronization mechanisms that make it hard. So, but right now, I'm not going to focus much on real-time programming. I think there are actually a couple of classes just covering that at ETH. And instead, I'm just going to give some further real-life examples to indicate how difficult it can be. The next level is to work on distributed computing. So it's very similar to parallel computing, but a little bit more specific on some parts. Parallel means that you can do many tasks at the same time. Doesn't say where. Distributed means it's actually more a technical detail, that you are not working on your own computer anymore, but it can be a lot of computers distributed all over the place. Sometimes it's just some local little cluster. Sometimes you go out on the cloud and you don't even know where the servers are standing and how big they are. You just buy in, say, 20 units and say, let's do something with it. And if you start working with distributed computing, there are some important things to think about. One is network delay. As soon as you go outside of the computer, you have to think about that there is a delay of transferring messages, data exchange between the different units in the distributed systems. And the other thing is also and then there's file system issues that you can, if many processes access the same storage unit, it needs to have some priority queue that tells where and which can access the memory right now or the storage right now. I actually haven't looked at the details, but I can imagine that the old traditional mechanical hard drives have more problems with parallel access than a solid state disk. But that's just an assumption because you need the mechanical switch between different places on the disk and the mechanical drive. And that gives more delays. And if you do too many accesses from different processes, the poor reader arm will probably be pretty confused after a while. Last thing is actually, I call it a human factor. You're not alone on the distributed system. And many people want to access it, and many want to use it, and you're placed in some kind of priority queue that, okay, now this guy can start his work, and now this guy can start his work. So all these things are problems that you have to think about when you start doing the distributed computing. So some examples of distributed computing, real world examples. So say you have 10 friends, and together they know all the capital cities in the world. And then you can have different approaches. To find a capital in a single country, you just have to yell the country and wait until someone responds. So in principle, all friends, they look in the memory, okay, I know, no, I don't. And then after a while, there is a response coming back. And the other one is to find the one who knows the most countries each in turn, and see how many countries they know, and you select the one with the highest, and that could be the one who gives you the answer. But that's less good, actually. And then you can also have a lot of friends, each has some money, and to compute the amount of money they have, they all have to bring in the information, and that's not really so efficient in the sense of distributed computing. And even worse is to find the median coin value of the people that you know. So you need to ask everyone how many about which coins they have, and you have to make one big master list, and then you have to find the median out of that. And that is not really a good task for distributed computing. And I already mentioned that one very large issue with parallel and distributed computing is the need to access the same resources at the same time. So we have memories and files, pieces of information, network resources, and then we come to something called deadlock, because everybody can read, sometimes not even that, but at the same time, two processes are not allowed to write at the same spot. And then we come to a classic anecdote in parallel computing called the dining philosopher's problem, where you have 6 philosophers sitting around a table and 6 forks. So far so good, possibly, but now comes an extra condition. Everybody needs 2 forks to eat. And to start with, each philosopher takes the fork to his left. So there are no forks left. Now is the question, who is going to let go of his fork in order to let someone eat? And how can you do it in the most efficient way in order to get the task done, meaning the philosophers can eat and not just talk and think? And philosophers have the tendency of discussing and philosophizing a lot. So if you have a bad design, you can really come in a deadlock situation that everybody is sitting there holding their fork and no one giving it away and nothing is happening. We are just idle waiting for the system. So this is something you really have to watch out for when you start designing a parallel program. So we have some challenges. So one of course, considering the dining philosophers, coordination. You need to coordinate how data is flowing between the computers in non-trivial parallelizable tasks. Second problem is also mutability. That is when 2 computers try to write the same information, and then you don't know really what is written, and that's not good. So you need something, a control barrier, and that's when you come to the blocking, that you have to have some blocking mechanisms around the memory that everybody can write on. And this can also then lead to the problems in the parallel code. And often when you have a parallel system with many computers, and you say, okay, I have 100 computers, I have a speed up of 100. So the task is done in 100 times faster. That's not true, because the speed up depends on the available resources. So we have the CPU, the memory, the storage, network. It also depends on the implementation of a code. I have done some Hello World parallel codes, and they were actually slower on 8 cores than a single core. And that is a kind of a racing condition within the memory that caused that. After some rearranging of the code, I could get a pretty good speed up. Not as many as I had the cores, but anyway, 5-6 times is reasonable on a normal CPU. And then comes the scheduling question. How are the tasks distributed among the resources? In principle, for that, the processes need to tell, essentially, or have a list of which resource they need, and then send that back to the scheduler. who then distributes the tasks in a way that it's most efficiently used. So what can happen if you look at this curve is that ideally you want some linear speed up, and usually also have with a number of CPUs. But at some point, that is when the resources are getting scarce, then the performance is dropping a little bit and dropping even more. And at some point, it's actually falling back. And that is when the resources are really, there is a fight about the resources. And that means the CPUs are just hanging around, want to do something, but they can't. And that can actually drop below the performance of 1. In these regions, you have less deterministic behavior on how the performance is. But how it performs, it also depends on what task the process have to do, how much exchange they need to do between each other. And that is then the question that you need to tune up, maybe not in the first round. And some of these things during a normal master project, PhD project, most people don't really care about it. They say, okay, I have a problem. Maybe I partition the data a little bit more, and then usually it's fine enough. Really hunting the problems around this, that's more into going into the software engineering, computer science, in order to improve the algorithms, the coding of the core code of the algorithms. So usually, if you see this tendency, it means you have a resource problem. Deal with it in a pragmatic way, unless you find the pleasure in coding on the low level. Other challenges is sending the instructions and data is far away. If you have many computers, then say you have 1,000 computers working on a problem and one fails. On the local workstation case, I would say if one problem fails, one part fails, you may crash your calculation. But if you have distributed computing, you can build it up to be redundant in some sense, and have watchdogs checking, okay, this one takes unreasonable long time. I ignore that and dispatch the task to some other nodes instead in the distributed net. So that is what the system should actually take care of when you have a good scheduler. And then is the question how you can access the data and process data on different computers, doing quickly and doing it without expensive infrastructure. And that is also a challenge to design your distributed system in a way that you can have maybe fractions of the data on one chunk and another fraction of data on another chunk. That reduces the cost of this, because the storage, when it grows, it is usually more expensive to handle than if you have a small one. There's probably some nice curves about how good it is to work at different sizes and what the costs involved are. Let's go to the programming now. There are different approaches on how to program a parallel system. So the imperative coding is probably the one you know by now. You do it in most languages, so like C, C++, Java, MATLAB. Exact order is given when to do stuff. Data management can be controlled manually. Also, job and task scheduling is more manual. And there is a potential to tweak and optimize the performance between the different steps. So just a little reminder from lecture 1, we had this making a soup example. So to make a soup, We need first to buy some vegetables. Then we need to buy some meat. When we got the ingredients, then we need to chop the carrots into pieces, chop the potatoes into pieces, heat the water, and then wait until the water is boiling. And with that, we can add the chopped vegetables. And after 5 minutes of boiling, we add some meat, and then we boil it until it's ready. So that's a soup. And as you can see, a couple of things here, they could happen in parallel. So we want to do that. And one way of doing it is work declarative. And languages like SQL, Erlang, Haskell, Scala, Python, and R, they can be coded in a declarative way. And then you more state the goal of what you want to do instead of the specific steps that you need to do. And the data is in this framework automatically managed and copied. And if you do it like this, it's like free hanging units waiting for something. And that makes the automatic, the scheduling is automatic, but may not be the most efficient way. So you declare you need to buy vegetables. So then you start to declare the task, chop veggies. Then you need to buy meat at the butcher. So you send off a task, chop meat. And then you come to a barrier point where you say you need to wait until the vegetables are available. And then you can start next task, which is chopping carrots into pieces. At the same time, you can also dispatch the next task, chopping the potatoes. Now you can start the next task, which is heating water. And then we have a new barrier point, which is the water is boiling, the carrots are chopped, the potatoes are chopped, and the next task is add chopped vegetables. Following that, wait again, now with a timestamp for 5 minutes, and then you can add meat. So this is a different way. You can draw a different flowchart graph from this. So this is just a table showing the two ways in parallel each other. And if you have one person, the second approach, the declarative, is unnecessarily complicated. I mean, you could possibly do the imperative maybe in a better way, but anyway, it's for one person, the imperative is probably better than declarative. But if you have a whole team in the restaurant, you could actually send some guy to buy vegetables, some guy to buy meat, and then the chef is standing there waiting until he can start chopping the different vegetables, and then you can actually have different resources doing stuff. They probably have one guy who is checking that the water is boiling, and so on. So then in this concept, you could actually make a soup faster than declarative. So if now you want still to do the imperative way, so how can you make it faster? Well, if you have the team, you can say that, okay, everybody starts chopping the vegetables now. And then they're chopping, chop, 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 chop. And of course, if you have a big pile and many people take from it, it's of course faster. So that would be the other way of doing it. And or else yet another way would be to say, each one of you get these resources, make a soup, and then each person is making his own soup. You can give different, you have different possibilities now. So you can, in the imperative, you can optimize specific tasks. You can say the chopping of vegetables can be done this and that way. The mixing can be done in this way, so that people can do it faster. For example, is computing the fast Fourier transform. That algorithm in MATLAB and Python is automatically using many cores, and of course the result is faster because the fast Fourier transform is really about splitting the tasks and then to reduce them into something afterwards. Then we can also do the soup example, that we are creating many soups at a time, and that can give us then the cluster-based computing, that you really send off the task. Could, for example, also be that you want to reconstruct a lot of CT images. That is really a perfect task for a cluster. You can just say, okay, you reconstruct those slices, you reconstruct those slices, and then you have everything ready afterwards. So then more or less the nodes only report, I'm done with my slice, give me some more. And then you pass through the data stack pretty good. Declarative, you can run everything at once. So you declare how to do it, and then you send off and things are happening. And in that case, each core or computer takes the tasks and run it and send it back when it's done. The execution order of all these tasks doesn't matter, because you have these waiting barriers where there is need for synchronization between the different tasks. Then as an option actually comes a little bit in the declarative thinking. So don't run anything at all. So only do something when it's needed. And you declare a lot of tasks, and when I need something, I kind of flag, I want that, and then something is starting to run. And that would be, for example, you wouldn't buy any tomatoes because they're not needed in final soup. So that would be the reason that even though you had defined buy tomatoes, it would never even be touched. Another thing about the parallel computing is that you have to, when you scale it up, you have to organize your data in a very good way. Otherwise, you will have a mess when you start running your program. And we have seen that many of our analysis produced text files, many text files possibly, and organizing these, you will have to name them in a good way with some structure and make sure that everything is right. After a while, it's even difficult to manage them for a human unless you have made a good structure in the data set. And languages like MATLAB and R, they are in general designed for in-memory computation. So it assumes you have everything available at the moment. Probably also toolboxes that can do some distributed computing, but the main concept is still for in-memory computation. And then the data sets can also have many parameters, and they can be complicated with cross-linkage between them. And also when you have these lists, so in the beginning, people are taking maybe Excel, and then they want to transfer it because they need more flexibility to write it up in MATLAB or R or Python. Then you really need to rewrite and rethink stuff from the way Excel is doing it into what MATLAB or R is doing it, or Python for that matter. Next thing is when you now have all these your parallel code or your program, you want to run it on some systems, then we come to Q processing systems, and that's, say, informatics organization of the cluster, that if you have some resources, that would be the computer's memory and storage, and you also have some network connections between them, and you only have them for a given time, because you may be only paid for 2 hours of your cluster or something. So those are the resources. And then you have your little program that are the tasks or jobs to be run. And then you can define what are the necessary resources to run this in order to reach it in time. Then you need to tell how much is it actually sucking out of the system, including how long time you expect it to take. And then we have the users, which are in this computer system are accounts that are submitting jobs to this queue system. And then it's up to priorities to make sure that not only one user is taking all the resources at the same time, but that you can actually balance it out so that everybody have a chance to get a little bit, and with that approach the solution faster. Because sometimes one user may need a lot of storage access, while the other one is doing heavy computations on the CPU. Those two can live together, and that is the task of a scheduler to make sure that it happens. So a cluster is essentially a bunch of computers, like the ones I have behind me today. And its design, or the structure, is that you have a master node, or maybe several master nodes, which are the access points to the cluster. So this is a point where people log in, and then in there you start the scheduler for your task, or you send your tasks to the scheduler. The worker nodes is the big working masses. So those are the many computers, and they're connected with each other, sometimes in sub-networks in order to balance the load in a good way. And finally, there is also the scheduler, which is sometimes a specific node, and sometimes it's just a part of the master node, depending on the size of the cluster. And this one decides, like in my examples previously, that CPU heavy and a storage heavy application, they can be run at the same time. So this is the main structure of a cluster that it's good to know about when you start sending things to it. And next step would be to talk about databases, but before that, I think we make a 5-minute break. So see you in 5 minutes, and let's stretch our legs and drink a little, and then it's fine. So I'll be back in 5 minutes.